Hi. For this video, what I'm going to do is talk a little bit about how we use the equilibrium constant to make predictions about chemical reactions. So thus far, what we've spoken about are doing some calculations where we try to figure out what the equilibrium constant is. So that's a common type of calculation. But perhaps even more common is that we know the value of the equilibrium constant and we want to make some predictions about the concentrations of the reactants and products, maybe just one, maybe all of them, at equilibrium. And that can be very useful information for us. So what I'm going to do is I'm going to start with a problem that involves doing some calculations. Where we're given information about the initial concentrations and then asked something about the equilibrium concentrations. Okay. So let's begin. We're going to do this qualitatively or semi-quantitatively at the beginning. So it'll be somewhat quantitative, but not full-blown calculations. Okay. So the first thing to mention about this type of problem here, which is called using an equilibrium constant to predict the direction of a spontaneous reaction, is that they neglected in the problem to use the equilibrium symbol, the double arrow for this. This should be a double arrow, okay? So a chemical engineer is studying the following reaction. This is a relatively famous famous reaction. It's called the Haber process. Nitrogen in its gaseous form, N2, is reacting with hydrogen in its gaseous form, 3H2, to form ammonia, NH3. So the stoichiometry is 1 to 3 to 2. And at the particular temperature they're looking at, the value of the Kp is 2.9 times 10 to the negative 4, right? So the engineer charges, that's a term that means fills, 3 reaction vessels with nitrogen and hydrogen, and lets the reaction begin. She then measures the composition of the mixture inside each vessel from time to time. Her first set of measurements are shown in the table below. Predict the changes in the compositions that the engineer should expect the next time she measures the compositions. Okay. So there are 3 vessels, 3 containers. One of them is called A. So we'll just look at A first, and then we'll do them each at a time. These are the 3 substances here. These are our initial pressures. Okay, so these are what we're starting off as. And then the question is, what is the expected change in pressure? Should it go up? Should it go down? Should there be no change? Okay. So let's take a look at this one. And I'm going to write this in a particular way. I'm going to write N2 and 3H2 is going to form 2NH3. Okay, now there's not much room here, but I will write down that K sub P is equal to the pressure of NH3 squared, right? Products over reactants divided by the pressure of N2 divided by the pressure of H2 to the 3rd power, right? Don't forget those exponents, right? The coefficients become exponents. And at this particular temperature, we have a value. Now I'm going to put it in scientific notation, 2.9 times 10 to the minus 4. Okay. Now, the question is, are we at equilibrium, really? So let's get into here. What they're saying is the initial. I'm going to use I for initial. That's what we're putting in. The pressure of nitrogen is 41. 38.89 atmosphere. The pressure of H2 is 47.76 atmosphere. And the pressure of ammonia is 38.67 atmosphere. So the only issue here is, are we at equilibrium? You know, so how do we tell? What you do is you calculate what we call Q, in this case QP. The actual calculation is done using these pressures. Q, by the way, has a name. It's called the reaction quotient. And mathematically, it's calculated in the same way that K sub P is calculated. It's the pressure of the ammonia squared, divided by the pressure of the nitrogen, divided by the pressure of the hydrogen cubed. Okay, but it can be done at any time during the reaction. Whereas Kp can only be, we can only calculate this value of Kp here if we have the equilibrium pressures. So we have to be told that it's at equilibrium. On the other hand, if we say, hey, we're putting this in, that's not necessarily at equilibrium. Initial concentrations or initial pressures typically are not the same as equilibrium. Okay. So these can be done with initial pressures. Now here's our rule of thumb. If K sub P is equal to Q sub P, then we are at equilibrium. And the pressures will remain unchanged, right? If you're at equilibrium, things don't change. The concentrations don't change over time. On the other hand, if K sub P is less than Q sub P, okay, so you have a smaller value of K and a larger value of Q, then the reaction will, quote, shift to the left. Now, the left side is your reactant side, okay? So if Q is greater than K, is another way of putting it, that's the more common way of putting it, then the reaction will go toward the reactant side. Okay, so I can do it this way. It goes in this direction if Q is greater than K, or K is less than Q. On the other hand, if K is larger, greater than Q, the reaction will shift, quote, shift to the right. Okay, go this way. That's if Q is less than K. Okay. Now, why is that the case? I'm going to just show you one quick example. Suppose I were to say A goes to B. And K would be pressure of B over pressure of A, right? Suppose I said, and let's give a value. K is 5,000, big number, okay? Suppose I said our initial pressures were 1 and 1, 1 atmosphere, 1 atmosphere. You would calculate Q as the pressure of B, so that would be 1 divided by the pressure of A, that's 1, that's 1. So Q is less than K, right? It's less than 5,000. What that's telling you is that this pressure here divided by this pressure here is too small. It needs to be 5,000, but it's only 1. So how do you make it larger? How do you increase it? You have to increase this number up here. This one's got to go up. But it can only go up if the one down here goes down, because a chemical reaction can only do 2 things, really. It can go this way, or it can go that way. It can't make both go up. It can't make both go down. it can only have one increase, one side of the equation, at the expense of the other, right? Law of mass action, right? We can't create or destroy matter. But if some of the reactant is converted into product, that will result in a higher ratio of products divided by reactants. And essentially what will happen is over time, it'll keep going until Q reaches the value of K. Once they're equal, it stops. It's almost like with an airline when they sell tickets. They haven't sold any tickets, but they've got 300 seats. What happens? They start selling tickets. So you get more people for the seats. Eventually, they're going to stop selling. Now, ideally, they would stop at 300, but they usually go to 330 or something like that because they assume some people will be willing to give up their seats and some people won't show up. But in any case, the point is once you reach the number of seats, you stop selling tickets. That would be logic, right? Same thing here. Once you get this ratio up to 5,000, it's going to stop, you know? So what will happen is some of this will go down and this one will go up, right? One goes down, one goes up. That's called a change. And then at equilibrium, it's 1 minus x and 1 plus x. You just take your initial plus your change. So you could imagine, you know, maybe, suppose I said x is approximately 0.99. I don't know, we'll see. What happens? Well, you would start off, A would start off at 1, but it would go down by 0.99. So now it would be 0.01. You've lost 0.99, almost all of it, almost all of the 1. On the other hand, B goes up because A is being converted into B. So it'll go up by 0.99. So now it would be 1.99. And so if you take 1.99 over 0.01, well, you get 199. So we're still not at 5,000, you know, so maybe it's really goes, instead of x is 0.99, maybe it's 0.999, right? And eventually it'll get there, okay? So let's take a look at this example here. I'm going to do the calculation here. All we really need to do is calculate Q. And if Q is less than K, the reaction will proceed to the right. You'll get an increase in the concentration of the product. On the other hand, if Q is greater than K, then that means there's too much product, and you'll essentially, the reaction will go to the left, and you'll have less product and more reactant. Okay, so let's calculate Q. It's the pressure, just be careful, it's the pressure of ammonia squared. So ammonia is 38.67. Remember, we don't need to worry about units for this. Don't forget to square it. Divided by the reactants, right? H2 is cubed. So N2 is 41.89. And H2 is 47.76. Okay, so make sure you know how to do that on your calculator, right? Actually, I can probably do this on the calculator here on the computer. So it's 38.67 squared divided by 41.89 equals, and then I'm going to divide it by, again, divided by 47.76, but now this is cubed. And so it looks like we get 3.3 times 10 to the minus 4. Okay. Well, it looks like Q is actually greater than K. They're not that far off, right? 3.3 times 10 to the minus 4 is greater than 2.9 times 10 to the minus 4. Okay, but it is greater, so it is larger. So if you have a larger Q, that means you have more products than you need. So that means the reaction is going to shift to the left. Now, what happens when you shift to the left? The products are going to go down. That's what that means. The products are going down. They're being converted into reactants. And the N2 and the H2 are going to go up. Okay, so coming back to our question, okay. our answer here would be that the N2 is going to increase, the H2 is going to increase, and the NH3 is going to decrease, right? Because the reaction shifting to the left, so that means you're going to get a change where the reactants increase until their values reach equilibrium concentration or pressure. The product's going to go down until you get down to that 2.9 times 10 to the minus 4. They probably won't have to change very much, just a few percentages, but they will change a little bit until we reach that point. Okay. Let's try the second mixture here. So now, again, we're going to still use the same value of K. What's going to probably change here is our Q, right? Because if you look at these pressures, they're all different than they were in the first set. Now, it's possible that that mixture of pressures, it could be equal to K. If it is, it's at equilibrium and there'll be no change. But if this pressure combination is greater than K, then what you would expect is the reactants to increase pressure and the products to decrease in pressure. Okay, so let's take a look at this one. It's really just a matter of putting in the numbers now. Okay, so I'm not going to put the states of matter. I'll just write out the balanced equation. Okay, and now we're going to use, here's our initial. Notice I'm putting initial in here. And this is 50.02. The H2 is 47. Oops, nope, sorry, it's 57.88. And then the NH3 is 53.05. Okay, so we're going to calculate Q. So that would be 53.05 squared divided by 50.02 divided by 57.88 cubed. Okay, so let's calculate that. So 53.05 squared divided by 50.02 equals, and then I'm going to divide it by 57.88, and I'm going to cube that one. And again, here we go. Oh, there we go. 2.9 times 10 to the minus 4. Guess what? Q sub P is equal to K sub P. Boom, got it. Awesome. They're equal. That means that the pressures will not change. Okay, we're done. We got that, right? So no changes there. So for the second one, part B in this particular problem, okay. This one right here, it just turns out those three pressures correspond to 2.9 times 10 to the minus 4, which means it's already at equilibrium. So there's not going to be changes in anything. Okay. So here we saw there were changes because Q sub P was greater than K sub P. Here we saw no changes because Q sub P is equal to K sub P. Well, let's look at the third one. What about the third one here? So here are our pressures. Just kind of estimating it, it looks like our reactants here are higher than they were in the first one. They're both higher. And the product is lower than it was in the first one. So it's quite possible here that we're going to have Q sub P is less than K sub P. Okay. But it's hard to tell with those kind of numbers, right? It's not like 6 and 2, it's 37.79. So we have to kind of go through and see it. So again, the equation is N2 plus 3H2 goes to 2NH3. remember that our K sub P is 2.9 times 10 to the minus 4. So now our initial pressures are, for N2, it's 42.28. For H2, it's 48.92. And for NH3, it's 37.90, right? So change equilibrium. We're going to get in the habit of doing that. So what we do is we calculate Q. So 37.90 squared, right? You have to square it, right? Because of the expression for K for this reaction. And then divided by 42.28. I'm just looking at the coefficients every time I do this. Oh, there's a 2, so we got to square it. There's a 1, so we just raise it to the first power. There's a 3, we got to cube it. My guess was this is probably going to be smaller than K sub P. So let's see. 37.90 squared divided by 42.28 equals divided by 48.92, and that's going to be cubed. So it looks like, well, you know what? It's still pretty much the same. Looks like it's about the same. It looks like we got a Q that's about 2.9 times 10 to the minus 4. So it looks like it's pretty much equal to K. Okay. I'm surprised. I thought that it would actually be, you know, a little bit lower. Okay. So remember, if Q is less than K, that means you're going to shift to the right. Products will increase and reactants will decrease. If Q is equal to K, then there's no change. And if Q is greater than K, that means the reaction is going to shift to the left. So the products will decrease and the reactants will increase until you reach equilibrium. Okay. So these equilibrium constants are interesting. They're like, you know, they're telling us something about what's going on, right? Like it's hard to interpret exactly what the molecular aspect of this. It turns out it's connected to energy, the energetics of reactants and products. But the K is then actually, we can use it to figure out what direction a reaction will go. Now, what we're going to do in the next step is we're actually going to do some calculations and figure out how much they change by using what's called an ice table. Okay, so let's take a look at that ice table. That is what's called setting, the problem is called setting up a reaction table. Okay, oops, put that on. Setting up a reaction table. Okay, so let's take a look at this one. Okay, setting up a reaction table. So here's what you have. You have 200 milliliter flask filled with 1.6 moles of NO2 and 0.4 moles of NO. This reaction becomes possible. NO2 is converted to NO plus O2. It's balanced. Complete the table below so that it lists the initial molarity of each compound, the change in molarity of each compound due to the reaction, and the equilibrium molarity of each compound after the reaction has come to equilibrium. Use X to stand for the unknown change of the molarity of O2, and you can leave out the capital M symbol for molarity. Okay, so this puts it all together. So here's going to be our logic, and they actually set up a little table for you here, which is nice for them. Okay. Here's what we do. We calculate the initial molarity. So notice they give you the volume and they give you the moles. Moles over liters is molarity, right? So we're going to do a little calculation of initial molarity. Then we are going to do a little calculation. Okay. A little calculation of the change. Now it's actually telling you a little bit about the change here. And then we're going to actually write out what the expression for the equilibrium is as well. So we're actually not really doing the absolute calculation. We're not doing the numerical analysis here. We're just setting up the table. Okay. So one of the things I noticed about this problem is they don't give you the value of K. So for that reason, they're just trying to tell you what's actually happening here, what direction the reaction is going. So if the change is X, that means it's generally considered positive, and the opposite side of the equation will be the opposite sign. So if you get a positive for O2, then you have a negative for on the other side for the NO2. So the sign should be the same on the same side of the equation. So if you have positive on both of these, you're going to have negative on the other. It's the reverse. Okay. So let's take a look. The first thing we're going to do is calculate the initial concentrations. Okay, so let me write the equation down. So the equation is 2NO2 goes to 2NO plus O2. Okay, so now let's do, the initial. We have 1.6 moles. Okay, and then for the NO is 0.4 moles. Okay, now if they don't tell us anything about O2, it must be, we have to assume it's 0. So no information given about one of them, it's just 0. Okay, so then they ask us to do the change and then the equilibrium. So they want molarities. So let's calculate molarities. They tell us that the volume is 250 ml. Okay, so let's do a conversion first. We're going to convert it to liters. Okay, milliliters to liters. So 1,000 milliliters is a liter. It's 1,000 to 1. Milli is 1,000. So there's 1,000 thousandths in 1. So 250 ml. And a liter is 1,000 milliliters. Milliliters cancel, so you get 0.250 liters. Okay, so there's your volume. So we divide the moles divided by the liters, right? Let me erase the C and the E because we need room here. Now, why do we divide it? Because molarity is defined as moles divided by liters. We have to have those units. So 1.6 divided by 0.25 is the same as 1.6 times 4. So that's 6.4 molar. That's pretty high concentration, actually. Okay, they said you can leave the units out. So let's do that. Let's do the second one. 0.4 divided by 0.25. That's the same as multiplying by 4. So that would be 1.6 molar, but we'll leave the units out. And this is 0. So if you divide this by 0.25 liters, you're still going to get 0, right? Okay, so there's our initial. So we filled out the initial. That would be right there. Then they tell us that the change here is X. Okay, so this is what we're going to do. They're really telling you the direction that the reaction is going. If X is on the right side, that means the reaction is going to the right. So this is going to go, I'm sorry, I didn't balance the equation right. This is a 2. So if this goes up by X, this is going to go up by twice as much. The stoichiometry is 2 to 1. So this will be 2X. I prefer putting plus 2X and plus X, whatever, they don't. And then if the products are increasing, the reactant has to decrease. So we're going to call this minus 2X. Now, why not minus X? Well, again, you have a 2 and a 2. They're going to have the same coefficient. This is a 1, so you put the coefficient there, 1X. Okay. Equilibrium, 6.4 minus 2X, 1.6 plus 2X, and then 0 minus X. Oops, 0 plus X. But 0 plus X is just X. So all I'm doing in the equilibrium step is I'm taking the initial molarity and then adding to it the change. Initial plus change equals final or equilibrium. So 6.4 plus a negative 2x is 6.4 minus 2x. 1.60 plus 2x is 1.60 plus 2x, and 0 plus x is just x. So really now, here's what we would do. We would say that since these are equilibrium values, we would now say that we need, well, let's write it out here. Concentration of NO squared, concentration of O2, concentration of NO2 squared, right? These are all at equilibrium. That's when K is valid. Q is valid at any time, but K is valid only at equilibrium. So since these are at equilibrium, we can substitute them in. So you say, okay, well, NO is right here. There's NO right there, 1.60 plus 2x. But we have to square it. So you take that in parentheses and you square it. Then we have to multiply it by O2. O2 is x. There's x. And then we divide that by NO2 squared. So NO2 squared is right here. And then we would square it there. They don't ask you to write the expression. I think a good idea would be to have them in this problem ask you to write that. That'd be kind of cool. And that would be useful. But to be honest with you, they don't ask you to do that. So I'm not going to ask you to do it. But that is what they're doing. Okay. I do want to show it to you in any case. Okay. So there we go. Looks like we're set on that one. So let me show you one more, because this is maybe an unfamiliar type of problem for you. Okay. Okay. Suppose a 500 milliliter flask is filled with 1.1 moles of CH4, 1.0 moles of CS2, and 1.4 moles of H2. So here are 3 of the 4 materials are in there. The reaction becomes possible. So, you have 3 of the 4. As long as you have 1 on either, well, okay, as long as every element is in there, you can get the reaction, essentially. Okay. So if you notice, they tell you there's CH4, they tell you there's CS2, and they tell you there's H2, but there's no H2S. So you ask, oh, well, wait a minute. If there's no H2S, how can this reaction take place? Well, we have the reverse reaction underneath here, right? The reverse reaction says that if you have any H2 and if you have H2 and CS2, they can go in the reverse reaction and form H2S and CH4. So the fact that H2S is 0 kind of tells you what direction the reaction is going to go. If it's 0, it's got to go up, right? You can't go down from 0. You can only go up. So if this one's 0, you know it's going to be a positive X on that side. And if you look here, the change for CH4 is X. Well, that's on that side, right? It's going to be positive on this side. It'll be negative on this side, okay, on the product side. So let me, we're going to do exactly the same thing we did with the previous problem. So let me copy. Oops, sorry. I'm not sure that you actually saw that. My apologies. Let me come back here. Sometimes I forget to put this up. So let me come back up here. So 500 milliliters is filled with a 1.1 mole of methane, 1.0 moles of CS2, 1.4 moles of H2. The reaction becomes possible. So there is CH4, there is CS2, and there is H2, but there's no H2S. So that means this is 0, which means that it's going to form from the products. The reverse reaction, the reverse arrow, says that if you have CS2 and H2, you can form H2 and H2S, but you'll also form CH4. So that's why the change on the CH4 is positive, is because if the H2S is 0, the reaction is going to go to the left. And so you're going to get positive X on the reactant side. And then you'll have negative X on the product side. Okay. So let's take a look at this one. Okay, so CH4. Now the Be careful, make sure that you know that you don't forget about the coefficients, because they show up in two places. They show up as the exponents for the expression of k and q, but they also show up in the table as like plus 1x or plus 2x or plus 3x or plus 4x. They show up actually in two places. Okay, so let's do our initial. I'm going to do the concentration. So they told us it's 1.1 moles of CH4, and they told us it's 500 milliliters. Okay. Oops, sorry. 500 milliliters. I'm not going to go through the conversion, but that's 0.500 liters. So that's the same as 2.2 molar. Okay, so there's your initial concentration there. This is 0 because they didn't give us any. Divide that by 0.500 liters. That's going to give you 0. The CS2 is 1 mole divided by 500 milliliters or 0.5 liters. That's 2 moles per liter. Again, it says leave the units out. And then H2, they tell us it's 1.4 moles divided by 0.5 liters. Well, that's 2.8. Okay, so there's your initial. And then the change, they tell us that CH4 is X. Well, that means that it increased. If it was negative X, that would mean that it decreased. So telling us it's X tells us the reaction is going this way. So if it's going that way, this one increased. Well, that means this has to increase too, so it's 2X. But if it's going to the left, that means these have to go down. The products have to go down. So this is minus X minus 4X. Remember, it shows up twice. It shows up in K and Q, but the coefficients also show up in this ICE table, reaction table. And then you get equilibrium. You just take your initial 2.2 plus X, right? You just add them together. Just add the initial and the change. 0 plus 2X. Let's not write 0 plus 2X. Just write 2X. 2 minus 2.0 minus X. 2.8 minus 4X. Okay, so I'm going to write out the expression for K. It's not P, it's actually QC, it looks like. So you do the first product. So first product is right here. So 2.0 minus X. Coefficient is a 1. Times the second product raised to the 4th power. 2.8 minus 4X. Okay. Divide that by CH4 to the 1st power, right? Its coefficient's 1. So 2.2 plus X. Second product has a coefficient of 2, so we're going to square it. And that would be 0 plus 2X, which is just 2X. Okay. And that's going to equal your KC. We don't know the value here. If we knew the value, we could then solve for X and do some cool calculations, but it's not given in this problem. Okay. So there you go. That is section 15.4. I'm sorry, 15.4. And the last type of problem is section 15.5, which is what we call Le Chatelier's principle. So we'll look at some Le Chatelier principle problems in the next video. And that should pretty much wrap up chapter 15, a general discussion of chemical equilibrium. That's really what we're talking about here. The next chapter is 16, which is acids and bases. So we'll start applying acid-base chemistry to the next subject, as well as equilibrium. We'll connect equilibrium into that as well. Okay, so take care.